Chapter 8, Section 3. Volumes of solids with known cross-sections. Here's an example. A solid has its base in the circle x squared plus y squared equals 9. The circle x squared plus y squared equals 9 has center 0, 0, radius 3. So the problem says this circle is the base of a solid. It's the bottom of the solid. So all you see here is the bottom of the solid. Cross sections parallel to the y-axis are squares. Cross section could be called a slice. So I'm going to make a red slice here. I made it parallel to the y-axis, like the problem said, parallel to the y-axis. If you slice the solid, any one slice like this red one, take it out of the solid, slice it and turn it sideways, it will have this shape. The shape of a slice, or the cross section, is a square. That's given. In any slice, so if I sliced it over here, parallel to the y-axis, this slice would have the same shape. Not the same size, but the same shape, because all cross sections are squares. That's given. So just think about one of these for now. We're going to find the area of this shape. It's a square. Then we're going to multiply by how thick it is, and we'll have the volume of this one slice. The area of this shape times how thick it is the volume. And then we'll say that every one of the slices will have the same volume. We say the word same because it will be in terms of x. So they'll all have the same volume. We'll just add all of them up, and we'll have the entire volume of the solid, whose base is this circle, and whose cross sections, every slice or cross section has the shape of a square. So the top of this one slice right here has an x coordinate that could be anything, because I could have drawn it anywhere, and a y coordinate, which could be anything, but, well, not really. At the top of this circle, y has to equal the square root of 9 minus x squared. So I could say x comma y, but it's better to say x comma square root of 9 minus x squared. Those are the coordinates of this point. At the bottom of this vertical slice, the x coordinate will have to be the same. All points on a vertical line will have the same x coordinate. And the y coordinate down here, because it's down here below 0, the y coordinate is negative square root of 9 minus x squared. That's what we got when we solved the equation of the circle for y. So the distance from here to here is actually any side of this square. Let's say this is green now. That is over here now. This side here, this distance, is a change in y. That means it's the y up here minus the y down here at the bottom. That's this side of the square. So the area of the square is this side times this side, base times height, length times width, whatever you want to call it. So this side of the square is radical 9 minus x squared minus minus, that becomes plus, plus the same thing. So it's 2 radical 9 minus x squared. That's this one side. This side will be the same because it's a square. So right here, This is the area of this slice, cross section. Any side is a change in y. The thickness will be a change in x from this purple dot to this purple dot right here. It's a small change in x, so we could say dx, change in x, delta x or dx. Right here is the volume of this one slice or cross section. It's the length times the width times how thick it is, the one slice. And then we say every one of these red slices will have the same volume. Same because it's in terms of x. Add all of them up, all infinitely many of them to fill this whole base up. And they get added up from -3 to 3. Because this is in terms of x, this region here has no slice or cross-section before -3 and no cross-section after 3. These are x, the smallest x and largest x attached here. There's 2 times 2, so we're going to make that 4 to the left of the integral symbol. Radical 9 minus x squared times radical 9 minus x squared is just 9 minus x squared. There's the dx, and there's a -3, and there's a 3. Next, I'm going to distribute the 4 to each term here, also the integral, also the dx. 4 times 9, that's 36. Integral, dx, and then there's a minus. Another 4, because distributing the 4. Integral x squared dx. 36x minus 4x to the third over 3. No plus c is written. We're integrating from -3 to 3. Everywhere there's an x, we're going to put in 3. 3 times 36 is 108. 3 to the third is 27. 27 over 3 is 9. 9 times -4. 9 times 4 is 36. Minus. Every x is going to be replaced with -3. 36 times -3 is -108. -3 to the third is -27 over 3 is -9 times -4 is +36. Distribute 108 minus 36 plus 108 minus 36. 108 and 108 is 216. -36 and -36 is -72. And 216 minus 72 is 144. This number is the volume of the solid that you can't see here. The solid has a circular base and cross sections, vertical cross sections are each squares. I'm going to do one more example. So the second example is the base of a solid is bounded by y equals x cubed, y equals 0, and x equals 1. So I'm going to make a region that has these 3 boundaries. Y equals x cubed, y equals 0, and x equals 1. So 3 boundaries make sort of a triangle shape. Y equals x cubed, y equals 0, and x equals 1. This region outlined in blue is the base of a solid. It's just the bottom. Each cross section perpendicular to the y-axis. This time the problem says cross sections are perpendicular to the y-axis. perpendicular to the y-axis. They're talking about this cross-section like this. That means perpendicular to the y-axis means horizontal. Well, this is a solid that you can't see. The blue is just the bottom of the solid. This green slice is a cross-section. The problem says the cross-sections are equilateral triangles. Cross-sections perpendicular to the y-axis, each of them is an equilateral triangle. So this is the base of the solid. This is a cross-section. I'm going to take that one slice out and turn it sideways to show you that its shape is an equilateral triangle. This is one slice. If you make a slice anywhere else, perpendicular to the y-axis, it will be a longer slice, but the shape of the slice will still be an equilateral triangle. The solid is coming out at you. You can't see it. And just like in the last example, we're going to figure out the area of this shape. Then when multiplying by how thick it is, that'll be the volume of the slice. Then we'll say every one of the cross sections of the same volume, so we'll just add them all up. That's the plan. So one thing you might have learned in geometry, or you might have never seen it before, that the area of an equilateral triangle is always one of the sides squared times radical 3 over 4. You might want to learn this formula if you don't know it already. Any side of the triangle, doesn't matter because it's equilateral. Square it, multiply by radical 3 over 4, you get the area. Take any one of the slices and label the endpoints with coordinates. When a slice is vertical, the top and bottom are labeled x comma something. Check it out, x comma something, top and bottom. When, that's in general. When slices are horizontal, each end of the slice gets labeled something comma y. Before the comma is always x. On this vertical line, everywhere on this vertical line, x is 1. On this curve, where y equals x cubed, everywhere on that curve, the cube root of y is equal to x. I could label this x comma y. I could label any point x comma y. But this x has to be the cube root of y. So something comma y at one end of the slice, something comma y at the other end. This side of the triangle, which is actually there also, is a change in x. It's left and right. It's a change in x. So that means it's 1 minus the cube root of y. That's the side of this triangle. If you square a side of the triangle and multiply by radical 3 over 4, that is actually the area of this cross-section. And the thickness is dy, because the thickness is a change in y. This is a very small thickness from the top of that slice to the bottom, and thickness is delta y, or dy if we want it to be really skinny. All horizontal slices have dy thickness. All vertical slices have dx thickness. Right here in this black and green, that's the volume of this. So we took the area and multiplied by how thick it is. If every one of these slices would have this same volume, we're going to add all of them up. And since we're working with y's here, this is in terms of y. Down here we have the smallest y in the blue region, and up here is the largest y. Because This intersection point, by the way, is 1, 1. And there's no y lower than 0 in this region, so 0 on the bottom. There's no y larger than 1. Make sure you understand we're using this 1, not the x. So I'm going to rearrange this and then put this in the calculator. I'm going to let's take the radical 3 over 4 to the left of the integral sign, leaving to the right, parentheses 1 minus the cube root of y. All of this is squared, dy, from 0 to 1. When you put this in the calculator, you'll get 0.043. If you do this without a calculator, which would mean you square this binomial, multiply 1 minus y to the 1/3 times itself, and then you'd have a few terms, distribute the integral sign, distribute the radical 3 over 4. If you take the time to do all of that, the answer comes out to be radical 3 over 40. So this is approximately the volume of the solid whose cross sections are equilateral triangles. And this actually is the exact volume. So there's two things you want to make sure you can do. Make sure you can get this on the calculator. Putting this in the calculator can be a little challenging. Also, I think you should try to do this without a calculator and see that you can come up with that answer. The end.